the vector equation of a line. So here, we're going to imagine a line going through the points A, R, and C. If it goes through the point A, you could make a position vector A. If it goes through the point R, you could make a position vector R. And if it goes through the point C, you could make your position vector C. So any point on a line has a position vector connected to it. How many points do you actually need to make an equation of line in 2 dimensions? 2. So if you only had point A and point C, you could make your equation of a line. And this is the idea. If you have those 2 points, if you have A and C, then A to C, this vector, A to C, is the direction your line is going. And if you wanted to get to any other point on your line, all you would have to do, start at your origin. Let's say I want to get to point R. I could start at my origin and go to point A, and since I know the direction of my line, I just have to go in that direction a certain distance, something parallel. This is the idea. If I wanted to get to point R as a vector, I could go to point A, and then I could go in the direction from A to C by some scalar distance, some proportion. Maybe more, maybe less. This is the idea of the vector equation of the line. The vector R will always be, you could go to any point first, and then go some proportion of the direction of your line. And we call that direction vector B. And the nice thing about the vector equation of a line, now unlike y equals mx plus b, you need a specific b, right? Y equals mx plus b only works if you have the y-intercept. The slope 0.1 is a little bit more like the vector equation of a line, because the vector equation of a line, you just need any random point. And then R becomes all the points on that line. So very much like the point slope form of the equation of the line, this uses any point, and the direction vector is kind of like your slope vector. Then you can take your vector equation of a line and write it in 2 other forms. And these forms let you connect to some of your old mathematics. So xy is any point on the line. You have your starting point, a1, a2, and your direction vector, b1, b2. The parametric form just looks at the components. The x component is a1 plus t times b1. The y component is a2 plus t times b2. This is called the parametric form of the equation of the line. If you take your parametric form and get t by itself, if you take your parametric form and get t by itself, you would get those two fractions. If you make those fractions equal to each other, you get your Cartesian form. Cartesian form can always be rearranged to y equals mx plus b. So you can take your vector equation and you can get back to your regular equations like you're used to, y equals mx plus b. The Cartesian form is called that way because on your Cartesian plane, which is just your basic graph, that's how you used to do it. So we've got a vector form, parametric form, and a Cartesian form. So, the vector equation of line, yes. The vector equation of line is quite simple. You want it passing through the point 2, 5 and parallel to this vector. So this vector's direction is 3 minus 4. So any vector that's going to be on this line, take that random point that you know, and it can be any point on that line. So vectors are free to have some options, and then your direction vector is going to be 3, -4, but you could write any multiple of that. It really doesn't matter. It could be 6, -8. As long as it's going in the right direction. And what we're saying is if I have the point A, which is at 2, 5. That's the vector A. This is the position vector A. And I know that my direction vector has to be 3 to the right and 4 down. So my direction vector, which I'm going to draw in purple here, 3 to the right, 1, 2, 3. 3 to the right, 4 down. This is my direction vector. This is my line. My line is a straight line in that direction. I can find any other vector that is on this line. So let's say I want to find this vector right there. That vector would be on the line. All I would have to do would be to travel along A, and then, oh, it looks like I'd have to go B, and then maybe another 3/4 B. So 1.75 times B, and I would get to that new point. And I can get to any point by just going in my direction vector by some multiple. And that's why we have this t here as a scalar. It's saying you can get to any point on this line by just doing all different multiples of our direction. This is the key. I'm hoping, is this making sense? Because this is the key to understanding this. To understanding that one random vector gets you a point starting on that line. Then our direction vector will make us travel along that line. If I wanted to get to this point here, to that vector, I have to multiply my direction by a negative to flip it in the opposite direction. And then some proportion of its length to get to the orange spot. So this t value can be positive, can be negative, can be any number, any fraction, any decimal. And then that moves you along the line. And this is the vector equation of line Now, we want the parametric form. We just look at our components. We're in 2 dimensions, so we'll have an x and a y component. You'd have 2 plus 3t for your x, and 5 minus 4t for your y. To get the Cartesian form, you're going to have to do some mental math to get the t by itself. Can you see in the first one, you can move the 2 over and divide by 3 to get t by itself. In this one, you move the 5 over and divide by -4. So we get our t's by themselves, and then you can just substitute. Since t is equal to both of those, you substitute in, and you get your Cartesian form. Now, just for fun, well, this is all fun, but just for extra fun, right? How would you write this equation of this line? You know that this line has a slope, right, of -4/3. Because it has a rise of 4 and a run of 3, and it's going downhill. That's your slope. If you wanted to write the equation, you'd probably go, well, I know I have the point 2, 5, so I could go y minus 2 equals m x minus 5. Agreed? And then if you wanted to, you could rearrange this equation to be y equals mx plus b. So I could have y minus 2 equals -4/3x, distribute plus 20/3, move my 2 over, and here is y equals mx plus b, assuming we didn't make any mental math errors along the way. I just want to show you that your Cartesian form, if you multiply it out, did I make a mistake? Uh-oh. I'm not happy about something here. Where did I make a mental math mistake? 2, 2, 15, 8.
Did you make the line work? Sometimes your lines by force.
Yeah, maybe. What did I do? Mental math mistake somewhere here. 4 times 5, 20/3, minus 2. Coordinate is 2, 5.
Maybe it has to make a mistake.
Yeah, I did it here. 18. Oh, I put the coordinates in the wrong spot, right? That's what you meant. That's like, yeah. This should be the.
I was like, wait a minute.
This should be y minus 5 equals x minus 2. Oh my goodness. What a rookie mistake. So then this would have been 8/3, and then add 15, get 22. Oh. I did it here, and I didn't make a mistake. You don't have to, but it's showing you if you took the blue part and you cross-multiplied here to simplify and rearranged it to y equals mx plus b, you would get the same equation that you would get with y equals mx plus b. Okay? What's the annoying part about y equals mx plus b? In this situation, lots of fractions. Right? Vectors says, why deal with those fractions? We can make life easier just by dealing with simple vectors. What's the vector form, in fact, is very similar. I would say the vector form is very similar to this form, but it also has fractions when you're dealing. And vectors are sort of like fractions because you write one number on the top and one number on the bottom, but all of your math is so much easier. So it's sort of like, oh, why do they teach us equations of lines like they do in grade 10? Because you're not ready for vectors. But now we have something that's like, oh, this makes my math so much easier. Okay. So this vector would be 3, 1. If it's perpendicular to that, in slopes that would be negative reciprocal, so we can write negative 1, 3, or we could put the negative on the bottom. It really doesn't matter where you put the negative. So your direction vector, yeah, I put it on the negative on the bottom this time. It wouldn't matter if you put the negative on the top. You take your random point on the line. Remember your arrow over your vector. And there we have our vector equation of line. Just nice and simple, no fractions, just points, just vectors. If you look at the components, you could write your parametric equation. The x component is always going to be 2 plus t. The y component is always going to be 5 minus 3t. And then your Cartesian form, can you get the t by itself? This one's going to be 2x minus 2. This one's going to be y minus 5 over negative 3. And basically, your Cartesian form is your y equals mx plus b form just rearranged. Once you get your Cartesian form, if you wanted to go back to your old school math, you could rearrange that and have y equals mx plus b. Okay? But we're going to find out that our vector form and our parametric form is going to be enough for us to solve almost all of our equations a lot easier than our old school Cartesian form. And the other beautiful thing is our old school Cartesian form does not work well in 3 dimensions. In fact, you've never learned it in 3 dimensions, so you could probably try to invent something, but it's going to be awkward. But with vectors, it's exactly the same rule. What's that? Okay, so what do you need for a vector equation of line? You need one random point and the direction vector. Again, I have the arrows over here. So any vector on our line will be a random point plus t times our direction vector. You are given 2 random points. You can put any one of them for A. It really doesn't matter. But we need to find our direction vector from A to B. And again, I'll draw out a little picture here. If this is my vector A, and this is my vector B, this is my direction vector from A to B. And you can think of it, I'm going to change these to lowercase. You can think of it as B minus A, but really, what are we doing? If I was starting at A, I would go negative A first, and then plus b. Intuitively, to me, that makes more sense if I'm traveling. If I want to draw a diagram and I actually want to travel from A to B, I'd have to go negative A first and then B. But the order doesn't matter, so if you're just using your formula, then B minus A is a nicer way to do that. This B minus A is the same as your slope formula, but a lot easier to figure out. So now I just take vector B, which is as a column vector 5, 8. 5, 8 minus 1, 4. Oh, do you do that sometimes? Accidentally add the fraction line? All the time? 1, 4. How easy is it to subtract them? 5 minus 1 is 4, 8 minus 4 is 4. So that's our direction vector, 4, 4. And your direction vector can be anything parallel to that. So you could decide to write 4, 4. If you wanted to, you could reduce that to 1, 1. If you wanted to be annoying, you could make it pi, pi, or EE. I don't know why you would want to do that, but you could. And so now we have any point plus t times a direction vector. And this direction vector, the 4, 4, could be 1, 1, could be 2, 2. I could have chosen the other point. Here, I made it negative 4, negative 4. Because that t scalar can be positive or negative in front, it really, as long as your direction is right, and it doesn't have to be in the right direction. You could go B to A. It would still be the same line. Right? Then we could write out our parametric equations. 1 plus 4t, 4 plus 4t. Or 1 plus 1t, 4 plus 1t. Solving for t, notice that you're dividing by 4 on both sides. If they were both 1s, it would be exactly the same. This one, in fact, is really easy. I can multiply both sides by 4. There's y equals mx plus b for this line. Y equals x plus 3. So a couple things. I think the direction vector is easier and faster than using a slope formula. Because the slope formula, you have to think about fractions here. You just don't worry about it. Just think about your x coordinates, think about your y coordinates. Okay? And then if you had to do y equals mx plus b on this one, you'd have to set up your equation, plug in a point, solve for b. This is almost faster just to use your parametric equation Cartesian form to switch it. I don't know if you get the sense, but I really like the vector equation. So we have time to do 1 in 3 dimensions. Is it harder? Not at all. So if P is 1, 5, 3, and Q is 2, 0, negative 4, can you see that your direction vector, you can either do Q minus P or P minus Q, it really doesn't matter. It's like, what happens if I screw up on my formula and subtract the wrong ones? It actually doesn't matter. So if you did Q minus P, you'd have 2 minus 1, 0 minus 5, negative 4 minus 3. And you get 1, negative 5, negative 7. If you did it the other way, you'd get negative 1, positive 5, positive 7, which would be parallel, and fine. Add your vectors. So using your classic equation of a line in 2 dimensions, how would you tell if a point is on the line? You'd plug it in and see if it worked. So now we want to find out, does this point lie on the line? Well, how do we plug it in? We plug that point in, and then the question is this true? Is there a t value that makes this true? So I plug in the point, and then I can look at my parametric equations and solve for t with each of them. So my x-coordinate says that -1 has to equal 1 plus t. That's my parametric equation for x. My parametric equation for y says that the 3 has to equal 5 minus 5t. And my z-coordinate says the 5 has to equal 3 minus 7t. And if I solve for t in each of those, I get different values. All 3 of those t values would have to be the same for it to be on the line. But since they're different, it's not on the line. What about 3, -5, 5? Plug it in. Look at your parametric equations. There's your first parametric equation. 3 would equal 1 plus t, and t would be 2. You look at your second parametric equation. Oh, I keep it waiting. And t would be 2. And then you look at your third, and t is -2/7. The classic teacher example does one where it works and one where it doesn't work. I just decided to do both that don't work. I bet you were, if that no didn't show up, I was like, in your head, you were like, if the first one didn't work, he'll show us an example of the second one that does work. What would I have to change? What would I have to put in for z to make it on the line? Right? Because it worked, t was 2, t was 2. If I wanted t to be 2 there, what would z have to be? This point is on the line. Sorry, you got it there? -11. Right? And this is as easy as just putting the 2 in for t. Right? What is 3 plus -14? -11. So if you had the point 3, -5, -11, it would be on the line. But both of the ones that we tried, and you have to check all 3. The t value has to work for all of them. So once again, if the t is inconsistent, then it's not going to be on the line. Awesome.